Dear students, in this session we are going to see about energy stored in a capacitor. Let us see that there is a charges plus q prime and minus q prime are present in the plate 1 and 2. So this is a capacitor. So the potential at this capacitor is V prime, which is equal to q prime by C. So this is a C is a capacitance of the capacitor, and q prime is a charge in the capacitor, and V prime is a potential difference, that is a voltage at this capacitor. Let us assume that there is a charge, the dq prime charge has to be moved from plate 2 to 1. That is the work done to move a small charge dq prime from plate 2 to 1. So there must be a small work done has to be done to move a charge dq prime from plate 2 to 1. That work done, which is equal to V dq prime. So let us remember that in what is the potential formula? V is equal to W by Q. So the W, which is equal to V by V into Q. So that V is a V prime and Q is a small charge dq prime. So the work is also small work done dW. So dW, which is equal to V prime dq prime. So dW, which is equal to, for the potential difference V prime, we have to substitute Q prime by C. That is Q prime by C dq. So what is the total work done? Yes, sir. Merely we have to put a integration symbol. So the total work done is integration of Q by C dq, that is Q prime by C into dq. So what is the integration? That is a summation. What is the work done to store the total charges in the capacitor? So the capacitor is a device used to store the charges. Capacitance is a ability of the capacitor to store the charges. So let us assume that initially there is no charge in this two plates, so the charge is 0. So what is the total work done to place a total number of the charge amount Q? So that is a Q. So the initially the charge is 0 and finally the total charge is Q. So the amount of total work done required to charge Q amount of the charge in this capacitor is integral 0 to Q prime by C into dq. So students, you understand that? So that means 0 represents initially the capacitor not at all having any charge. This Q represents the total, what is the desired amount of the charge we have to require to charge in this capacitor, that is a Q. So that is we have to take it as a lower limit and upper limit. Then you take the 1 by C outside, integral 0 to Q prime dq. So integration of x dx is equal to x squared by 2. So just you substitute here it will get in the next step q prime squared by 2. Then the limit, the lower limit and upper limit will comes to that this side. So lower limit and upper limit. So just you substitute the upper limit minus lower limit, that is the formula. So instead of q prime you have to substitute q. So q squared by 2 minus, instead of q prime you have to substitute 0. So 0 by 0 squared by 2, it is a 0. So finally we get this work done will be stored as a potential energy, that is a energy. So that energy, which is equal to Q squared by 2C. We can write this equation as a 1 by 2 CV squared and is equal to 1 by 2 QV, merely substituting Q is equal to CV. Let us see that Q is equal to CV. If you put a CV means C squared V squared. So C and C get cancelled, we get 1 by 2 CV squared. Also for C, Q by V. So C is equal to Q by V. Here you substitute Q by V. So V will come to the numerator and Q and Q get cancelled. We get 1 by 2 QV. So by substituting this formula in this equation, we get these three. So the energy stored in a capacitor is simply Q 1 by 2 Q squared by C, or 1 by 2 CV squared, or 1 by 2 QV. So it is a very simple question. Initially we take the charge is 0 and finally the charge is Q. So only we will take the integration limits as a 0 to Q. But whenever we start this question, we are assuming that some amount of the charge is present in the capacitor. In the middle of the question we are started, but in the integration form we are completed that 0 to Q as a initial one. Let us see for that, what is the energy stored in a capacitors connected in parallel? So we should keep in our mind, whenever the capacitors are connected in parallel, the potential difference, the voltage is constant. So what is the energy? U is equal to 1 by 2 Cp V squared, because the potential is constant. So we take this formula, V is a constant and P means it is a parallel combination. So I will put P. So what is the parallel combination of 3 capacitors or 5 capacitors? It is C1 plus C2 plus C3 etc. So 1 by 2 C1 V squared, C2 V squared, C3 V squared, like that is a 1 by 2 C1 V squared plus 1 by 2 C2 V squared plus 1 by 2 C3 V squared etc. So it is energy stored in the first capacitor plus energy stored in the second capacitor plus energy stored in the third capacitor. So the total energy storage is equal to addition of the individual capacitors energy. Let us see the same thing for the energy stored in the capacitors connected in series. If the capacitors are connected in series, we have to remember that the charge is constant. For parallel, the potential is constant. For series, the charge is constant. So U is equal to 1 by 2 1 by Cs Q squared. Here we will take this formula. So for the parallel combination, the potential is constant, we take this formula. For series, the Q is constant, we take this formula. So we have, for the both the formulas, we need the C values. So that's why we are taking that 1 by 2 1 by Cs Q squared. For Cs, here in the denominator C, I will put the suffix X for the total, that is the effective capacitance of the series combination of the capacitors. So 1 by 2, here it is a 1 by 2, so 1 by 2 Q squared. For 1 by Cs, we have to substitute 1 by C1 plus 1 by C2 plus 1 by C3. So 1 by 2 Q squared C1 plus 1 by 2 Q squared by C2 plus 1 by 2 Q squared by C3. It is a mere the energy stored in the first capacitor, second capacitor, third capacitor. So the both the equations have the same expressions. That means, hence we are come to the conclusion, the total energy stored is merely additive in both series and parallel combination of the capacitors. Either the capacitors are connected in series or parallel, the total energy stored in the capacitors is the combination, the addition of the individual energies stored in the individual capacitors of the capacitor.